Is my screen sharing?
Yes. And he'll tell us about the secret topological life of shared information. So please, Tom.
Thank you, and thanks to the organizers for putting this together. So I'm going to give a talk that's a little bit more quirky than the usual sort of talk that's given in string math, but hopefully it'll be sort of an interesting thing for everybody, and I hope it could be of use to you. So I'll be talking about a particular aspect of shared information, particular topological aspects that maybe you haven't heard of. And so we'll begin with the data of a multipartite state. And so this can be a state on the tensor product of some Hilbert spaces, or maybe a density state on a tensor product of Hilbert spaces. Or if you're not a hardcore quantum mechanic, you can consider something like a probability measure on a product of finite sets. So here, omega just denotes a finite set. And from this data, we can compute the mutual information, so the information shared among all the subsystems. So here, P indicates the sort of primitive tensor factors of the system, the primitive subsystems. And if P is equal to 2, and we're considering bipartite states, for instance, bipartite mutual information has become somewhat famous recently in the holographic literature. And you can actually generalize this to a multipartite version of shared information. And in general, it's a real valued quantity. And the claim of this talk is that this is actually categorified. So that means that there exists some graded vector space in this instance for which the Euler characteristic behaves like mutual information, or it actually is mutual information. And the cool thing about this is that while mutual information tells you about how much information is shared, this graded vector space tells you exactly what information is shared. And it might actually be non-trivial even when the mutual information vanishes. So bipartite mutual information usually doesn't vanish when there are non-trivial correlations, but the multipartite version can. And that's just like how the Euler characteristic of a topological space can vanish even when there's interesting gluing. It's a non-trivial topology. And in fact, there is sort of a non-trivial, non-commutative geometry or topology associated with this multipartite state for which cohomology captures this graded vector space. And the Euler characteristic of that non-commutative geometry is mutual information. Okay, and so for those of you who don't like or field theorists and or worry that this only applies to tensor product systems, it can also be applied to something in field theory, which is something like a local net, which is just an assignment of C-star algebras to causal diamonds or spatial slices of space-time. And this doesn't necessarily have a tensor product structure when you're considering multipartite objects. But all the technology here applies there. I'm just focusing on the tensor products version of the story just for examples. Okay, so let's go back to our little diagram where we associate this graded vector space to an n-partite state. And I'll denote the graded vector space by hk of the n-partite state. So that's the kth graded component. And this is just knowing that it looks like cohomology. And this will capture tuples of k+1 body operators that exhibit some non-correlations, non-local correlations between subsystems. And so here k+1 body just means that the operators only act on k+1 tensor factors, not trivial on k+1 tensor factors. And then we'll mod out by some sort of trivial correlations. So there's some operators that look like they exhibit correlations, but there's something like the identity operator or something silly. Okay, and this cohomology is great, or this graded vector space is great because it vanishes whenever we have, for instance, a pure factorizable state. And it also captures something like EPR pairs. So here I have the Bell state, a very simple entangled state on two subsystems. And this is a pair of operators which are sort of completely correlated. So these are two observables such that if you A measures this observable and B measures this observable, their answers are always completely correlated. And this cohomology captures all such observables. In fact, they might not be observables, they can be more general operators, but it also captures all of the observables as well. And more generally, if I have a bipartite density state, I'm going to, that cohomology is going to be generated by pairs of operators, RA and RB. So here I'll denote an operator by R just to indicate it's supposed to be interpreted as a random variable. And these two things are in the cohomology if and only if they obey this relation, which is saying that, well, if these two things were self-adjoint operators, it means that you can always replace RA with RB. for all purposes of computing correlations, or even just, it's saying that RA and RB are maximally correlated in the sense that this EPR pair is correlated. Sorry, this is, I have to resize my window here. Sorry for the technical issue. That wasn't apparent when I first began. Okay. I'll just do this now. Okay. So what could this look like for higher cohomology? So let's consider a tripartite state. Well, the cohomology is going to capture triples of operators in this sense, where here RAC is just an element of the algebra associated to the subsystem AC. And these things will obey some linear relation like this. And the twiddles just mean that we have to lift these operators to the whole ABC system in order to make sense of this relation. And this twiddle, it also means that this twiddle, the other twiddle, means that they're maximally correlated in the sense that I described on the previous slide. Okay, so just to make this seem like it's a real thing, here's an actual example of a non-trivial cochain in the cohomology of the GHZ state. Okay, so why is this cool? Well, as I sort of mentioned at the beginning of the talk, I alluded to, cohomology has advantages over mutual information. So the bipartite mutual information, which is a alternating sum of entropies, measures some information shared by A and B. And it's a pretty good measure because it's non-vanishing whenever you have entangled states. And you can generalize this thing to the multipartite situation in a particular way. So what you do is you take this inclusion-exclusion sum pretty seriously, and you get an alternating inclusion-exclusion sum, just generalizing it. There's more than one way of generalizing bipartite information, but I'm going to be considering this version. And this in general is a real number. And it's supposed to measure the information shared by every subsystem, but unfortunately it's a little unreliable. So if I calculated this thing for these two entangled states on these tripartite entangled states, it vanishes, which sort of makes you think that, well, perhaps one system sort of splits off, it factorizes. But it doesn't. We know these things are entangled. On the other hand, the cohomology does capture something interesting here, and it'll tell you about the non-locally correlated operators. And so let's go back to this picture where we assign a geometry to the n-partite state, so one level higher. Directly from this geometry, we can calculate an Euler characteristic, and I'll just demonstrate how you can do this. And it turns out that the Euler characteristic is not just some integer. The right idea is that it turns out to be some holomorphic function. It's actually a holomorphic function in 3 parameters. So it has a lot of data in it. And this thing I'm just calling the state index. So it's just an Euler characteristic of some form. And from this holomorphic function, you can recover mutual information by taking some limits. But on the other hand, I can take some other limits, and I get actual integers. And these should be the Euler characteristics of some complexes of vector spaces, which are the Euler characteristics of the cohomology I was talking about. So the state index encapsulates a lot of information behind it. Okay, and so we should think of this vanishing of this multipartite information on these states, while the non-vanishing of cohomology is analogous to how, when you take the Euler characteristic of a compact 3 manifold, you always get 0, so it doesn't tell you anything interesting. But the cohomology could be non-trivial because you have non-trivial compact 3 manifolds. So the idea is that cohomology only detects the number, Euler characteristic only detects the number of things that are glued together. And so for 3 manifolds, Poincare duality tells you, oh, you always have to get 0, but the cohomology can actually detect the gluing data. So just before we start defining things, I should mention that this is talk about basic quantum mechanics. Let's go back to our graduate school days and keep an open mind about things. There's very little input physics, which you might consider a bad thing, but it's a great thing because it's so general. And so there's no a priori geometry on any subsystems or tensor factors. I'm not talking about ADS CFT or anything holographic. It's just everything sort of emerges out of just basic linear algebra. And I think this generality means there's something deep there. And one almost immediate application that I can think of is that you can actually generate link invariants in this way from this technology. So if you take a link inside of the 3-sphere, for instance, and I consider its complement, which requires a choice of framing or a tubular neighborhood, but let's just choose one. Well, if the link has n components, it lives in the tensor product space assigned to the torus, if I consider this on Chern-Simons theory. Okay, so I get a pure state in Chern-Simons with some gauge group given by this assignment here, and it lives in the tensor product of Hilbert spaces assigned to the torus. Okay, and now I can just use the technology I talked about, the cohomology, to generate Poincare polynomials, for instance, or just compute these state indices. And these quantities are invariant under the choice of a frame. And so they're link invariants. And I honestly don't know if they're related to anything known. So there's also some closely related work along the lines of the ideas in here. There's this cute little paper of entropy as a functor, which has some sort of ideas that I also bring up. There's the most closely related work is by these fellows, Pierre Bourdeau and Daniel Bennekin, which talk about how mutual information in the classical world of probability theory actually arises as sort of a characteristic class. So they don't say it that way, but this is what they're saying. It's some obstruction theory thing. And their student, J.P. Vigneault, actually provides a nice exposition of this work. And this should actually tie into my work if it needs to be rephrased in a more modern language of obstruction theory to see the connection. I'm hoping to do that in the future. Okay, and then some folks also talk about applications of homotopy techniques to probability theory, and that has the same sort of flavor of what I'm talking about. Okay, so I should describe what a state is in my talk. It's something very general. So I'm just going to think about positive linear functionals on algebras, which are the expectation values of some measure or some density state, for instance. And if you want to get technical, I'm really generalizing everything to infinite dimensions, and I'll be focusing on finite dimensions, but you can generalize most things to infinite dimensional situation with von Neumann algebras. And technically, I'm using the abstraction of a W-star algebra. So you can use these two interchangeably. So for instance, if you're a pure quantum mechanic person, I can just consider this algebra, which is the algebra of random variables, to be bounded operators on a Hilbert space, and you get density states. On the purely classical side, I can consider functions on a finite set. And there, the state is just a measure on that finite set. I can consider the infinite dimensional version of this. Or I can consider sort of a quantum classical mixture, which is just a product of matrix algebras. So all finite dimensional W-star or C-star algebras look like this. And a state on this thing is just effectively the same as a tuple of density states. So one density state per factor of the matrix algebra. And this example, even if you don't care about quantum classical mixtures, sort of, if you look deeply at what some of the things I'm going to say, emerges naturally, even when you consider just the purely quantum mechanical situation. So keep it in the back of your mind, maybe. And it actually specializes to this case of the purely classical situation when you consider only Hilbert spaces that are one-dimensional. So you just end up with a measure on a finite set. Okay, so what's a bipartite state? Well, it's just the data of a pair of algebras and a state on the tensor product of those algebras. And when I want to be lazy, I'm just going to denote this with this whole set of data by an underline, and then maybe the subsystems that it lives on. Or I'll just say that rho is a bipartite state on this tensor product. And well, I can pull this state back on this tensor product using these to the individual algebras associated with the subsystems by using the tensor bi-identity maps. And this gives us reduced states or partial traces, or if you're talking about measure theory, the reduced measures, it should be, say, reduced on all the subfactors. Okay. So this is the real structure of what I mean by a bipartite state, is these pullbacks. It's not necessarily just the tensor structure. And we say this thing is factorizable. Well, if it factorizes as a tensor product of its linear functionals, and there's some normalization factor if we consider unnormalized things. And well, a pure state is factorizable if and only if its functional is factorizable. And in the classical world, the question of factorizability is about the question about independence of random variables. So similarly, you could talk about multipartite states. It's just the data on a tuple of algebras, data of a tuple of algebras plus a state on that tensor product. And similarly, I'll denote that by an underline. And again, for any subset, now I can pull back that state to the algebra associated with that subset. So you just take the tensor product over the subset. And I'll denote that by rho sub t for the subset t. And I should also mention, because everything in this talk is sort of functorial, everything is invariant or equivariant under local automorphisms. So these are just transformations of the state by a tensor product of an automorphism on each of the primitive subalgebras. So in particular, this is like changing a state under local unitary transformations. I'm actually considering things that are more general than unitaries that can be invertible instead, but you can actually change the story up and just talk about unitary transformations as well. Okay, so let's see why geometry should be associated to a bipartite state. And this diagram is sort of helpful for seeing that. Well, the idea is that if our state is factorizable, if I want to compute the expectation value of any operator, if I decompose that operator in the tensor product basis, I can basically just glue together expectation values on the local of local data, of local expectation values. So if I just know all the expectation values of the reduced states, I automatically know how the full state acts. So an obstruction to this descent of expectation values is basically encapsulated by pairs of operators that don't factorize in this way. And so that should set off your homological alarm bells. I use this this language obstruction I used it intently. And so you should expect that the cohomology captures these obstructing operators. So, and more precisely, it turns out that it actually captures those operators that are maximally correlated. So just not vague statistical correlations, but maximal correlations. And then I mod out by, for instance, the trivial correlation, which is just the two pairs of identity operators. Okay, so let's go back to mutual information and get another inspiration for why there should be some geometry behind this. So here is our bipartite mutual information. It's a positive real value quantity. And if you want to know the details, I can define entropy for a state on this product thing like this. And this is the same thing as the Iraqi entropy for finite dimensional algebras, for instance. And it generalizes the notion of a Shannon entropy and von Neumann entropy. So I just take the sum of all the von Neumann entropies on each individual density state. Okay, and so I'm only going to be talking about normalized things here when I talk about entropies. You can generalize entropy to non-normalized things, but it's getting a little funky in terms of physics. And I can take this, as I mentioned before, I can take this inclusion-exclusion sum and generalize it to define multipartite mutual information. And it's not going to be a positive value quantity anymore. But the nice thing about it is that it can detect whenever the state factorizes. So if I have a tensor product of multipartite states, for instance, an n-partite state and an f-partite state here, this tensor product is n times f-partite state, it will vanish if it's a tensor product. So this thing will vanish if any system decouples. And so it's a good detector of decoupling. And so the converse of that is that you have to have something non-vanishing, that it means nothing could decouple. And well, we know for the bipartite mutual information, the converse holds true. But for more than 3 subsystems, as I mentioned before, you have tripartite informations that vanish for n greater than 3 more generally. And you could just actually it vanishes on a whole family of states. And well, that's not a great thing. So let's try to understand what's going on there. Well, the idea was that it comes as an Euler characteristic, and maybe I can generalize that Euler characteristic as coming from some cohomology. So in fact, it looks like an Euler characteristic, and this might be a superficial observation, but it turns out to have a very deep meaning. And you just sort of reorganize this sum in a particular way. And it looks like, well, if there is some geometry associated to the state, perhaps this quantity here is the dimension of some kth component of the geometry. So I'm thinking of the geometry of the state as built up something like a CW complex or a simplicial complex, or maybe even a chain complex. So here, this can be just the kth component. And this fellow is the dimension. And so it encodes all the data about the partial traces here. So this I just want you to keep in mind. So this is just some vague observation. So let's try to make this more precise. Let's assume that there is some geometry, and we have to figure out what's the Euler characteristic associated with that thing. Well, first I have to tell you what I mean by Euler characteristic. And by that, I'm just going to be very general. So I'll just consider a category of some geometric objects. And all I really need here is a tensor category and some ability to glue those objects together. So if you know what this means, a push out, you have all push outs. And then an Euler characteristic valued in some ring, this should be a D, sorry, this is a ring D. An Euler characteristic valued in some ring is just an assignment that takes in isomorphism classes of those objects and outputs elements of the ring. And it should play nicely with tensor products. And it should obey this inclusion-exclusion relation whenever you have gluing. So here, X and Y are objects, and I'm gluing along Z in some sense. And it's just this inclusion-exclusion sum. But notice that it doesn't care about the details about the gluing along Z. So that's both a good thing and a bad thing, because we're losing information, but also it makes it easier to compute. So I can probably glue X and Y many ways along Z, but it doesn't care about those. And you can phrase this in a different way. You can just say an Euler characteristic valued in the ring D is just a homomorphism out of the Grundy group of the category. So that's the same sort of concept of these relations. Okay, so some quick examples. You take this idea on finite sets. This is just the Euler characteristics of the cardinality. Finite vector space's dimension. If you take graded objects, you get these alternating sums. And those are valid Euler characteristics. But I could also get things that look like Lefschetz indices. So if I consider, for instance, some category generated by pairs of vector spaces and endomorphisms, and I'm not describing the morphisms, but you can write down some pretty natural things and you always get the same sort of Euler characteristics. Here, a good family of dimensions is just given by the traces of powers of the endomorphism. Or you can just think of this, actually, the whole dimension is collecting into a function on the positive integers. And then I can also get Lefschetz looking things if I take graded versions of this. So let's go back to our category of, well, we're going to suppose there's some category of multipartite states. And perhaps this geometry that we're assigning to the multipartite state is just some tautological functor. And so really, what I'm saying is that the category of multipartite states is perhaps the geometric category we want to consider. And that just means that we can compute this Euler characteristic directly in terms of the multipartite state, without first having to understand the geometry associated to it. And now, to sort of understand how this Euler characteristic might look, we use a little bit of intuition here, and we can think of the bipartite state as being glued together by unipartite states, the reduced states, along the system AB, using the data of rho AB. And so this little identity, you could just write down with this sort of diagram. And here, these are Euler characteristics of unipartite things. And we can just repeat this recursively for n-partite states to express everything in terms of unipartite states. So just Euler characteristics of states on a single system. And well, okay, it's already starting to look like mutual information, but that's just because it's an inclusion-exclusion sum, nothing fancy there. And it's actually convenient to think of the dimension of a state as sort of the Euler characteristic on the unipartite thing. There's no alternating sums, it turns out, for these things. So it's just a change in notation. And if I want the Euler characteristic of multipartite things to factorize, the dimension has to factorize in a nice way. So let's take a guess at what this dimension is. Well, you want this to look like mutual information, but unfortunately, entropy doesn't obey this relation. It obeys this with a sum. So you say, oh, well, okay, I'll just take the exponential of the entropy. But that actually also has its own set of issues with playing nicely with the inclusion-exclusion sum. So more generally, you can look at this for a while, and you can write down something very general that does work. And it's this fancy-looking quantity. And it depends upon three parameters, alpha, q, and r. And it's just given, so there's a lot of data going on here. the thing to sort of note is that it looks like one of these Lefschetz indices where I can take arbitrary powers of this state. And so here, since everything is positive semi-definite or positive, this makes sense on all complex numbers, and it becomes an everywhere holomorphic function. And I can extend this to states on a finite dimensional algebra by just taking the sums of the individual dimensions of the density states. Okay, and so with this in mind, I haven't gotten to multipartite information yet, but I'll show you where it comes from. We can define, it's actually somewhat convenient to introduce the density state on the empty system, which is just the identity operator, maybe with some rescaling if we're talking about non-normalized things, and then there's some silly sign. And it's basically the same thing as the Euler characteristic. It obeys this nice relation. It obeys some nice gluing relations. But the cool thing is that if you rescale it and take some limits, it captures mutual information. So in general, this rescaling gives you this alternating sum where the entropies are replaced by deformed versions of those entropies. And here I'm calling this the Solis-Rainey deformed version, depends upon two parameters, because certain limits recover the Rainey entropy, which is pretty famous, and they also recover this Solis entropy, which has been a little neglected in the literature. And if I just take the limit q that goes to 1 of this thing, no limits on R are required, I recover the standard classical mutual information. So here's a diagram showing that. There's a lot of things going on here, but the thing just to note is I can start from this state index, which looks like an Euler characteristic of something through our vague discussion, and I could take a limit and get mutual information. But if I take another limit of these parameters, I start getting integers. And so we might think that there's some vector space associated to the state where this dimension quantity captures the literal dimension of that vector space. So in fact, there's a certain thing that assigns a vector space to a state, and that's the GNS construction. So let's talk about that. So recall that the GNS construction is just a way of assigning a module for a particular algebra given a state. And the way you do that is you just take your state, you look at this ideal of vanishing vectors with respect to that state, and you quotient out by it, and you get a left module. And just as examples, this will look something like functions. This should be a mu here. If I have a measure on a finite set omega, this is canonically isomorphic to functions that are on the non-vanishing points of the measure. And in finite dimensions, this is just some easy-looking vector space in terms of the density state. And the dimension actually turns out to be given via specialization of this dimension function. Okay, so we're on the right track here in terms of figuring out whether or not these Euler characteristics come from complex of vector spaces. So how do I get this complex of vector spaces? Well, you can actually, here's the fancy stuff. You can actually get this by looking at the GNS construction as a functor. It elevates to the level of a functor. And so you can define a category of states, and you can think of these as the unipartite states. And it just takes you into some category of representations. So here the objects are just some states. And on the other side, I get algebras and left modules. So the algebra can vary on both of these things. And the morphisms you should just think of as partial traces on the state side. Really, they're duals of algebra maps in some sense. And on this side, I get algebra maps and intertwiners. And both of these categories have nice notions of products and coproducts. So here it's just the product of both the algebras and the modules. And on this side, you get some sort of classical sum. And you can think of this as sort of like, these sort of quantities will arise even if you're a pure quantum mechanic, if you're considering, for instance, super selection sectors or measurements of a subsystem. These classical sums can be somewhat convenient. Okay, and well, how this thing acts on morphisms, if you know these terms, it's actually related to relative modular flow. But the thing I want you to focus on is that it actually takes these coproducts to products. And if you look at what a multipartite state is deeply, you can also think of it as a functor into the category of states. So it's sort of like a pre-sheaf. And it takes a subsystem into the reduced state. And then for an inclusion, so this is the category where the objects are subsets and the morphisms are inclusions. It's just a poset. And it reverses the inclusions by considering the partial traces over the complement. And then, so from this construction, you could just use check theory to construct something that looks like this. So this is called a simplicial object. So basically, if I start from a multipartite state on all subsystems here, I just take the traces over all one element systems to get a bunch of partial traces. And so this is all fancy. I don't expect you to understand exactly what it is, but the point is that this is our geometric object associated to our state, our multipartite state. And the kth component is given by this classical sum of the reduced states. And if I take the Euler characteristic of this thing, well, this is how we recover our state index up to some sum. And so, yeah, I'm also including this extra augmented piece of the empty state on the empty system. Now, how do I get a chain complex from this thing? Well, this is where the GNS construction comes in. I take this, and it just reverses all the arrows. But now each of these things is just a module. So something more realistic. And then I just forget about the underlying algebra, the module stuff, and I just think of them as vector spaces. And I take an alternating sum of these arrows. And it turns out I get a chain complex out of that. And so you should think of GNS of rho t as a subset of the random variables on the system T. So there are particular types of random variables. You're quotienting out by trivial things that you can't detect through the state. So what does this look like for the bipartite system? Well, it looks something like this. The point to focus on is that this differential just looks like this sort of this tensor product with the identity, and then I take a minus sign between the two. And so if this vanishes, it just means that one tensor B and a tensor 1 are sort of like the same thing. The state cannot detect the difference between the two. So they're maximally correlated in that sense. So that's what the zeroth cohomology captures. And for a pure bipartite state, you can actually compute this thing explicitly, the cohomology, in terms of the Schmidt decomposition. And if you're wondering what the first cohomology encapsulates, well, the dimension is a measure of how far the thing is from being maximally entangled. So there's a whole commutative version of the story on measures. And it turns out that the GNS construction actually gives you a commutative algebra when you're considering just commutative objects. And then I can use a version of spec to recover a set from each of those algebras. And the result is that you get something called a simplicial set. You can just imagine it as a simplicial complex. And the state index of this actual topological thing, just its standard commutative geometry, is just a deformation of the Euler characteristic of this that takes into account the sizes on each of these simplices. So the weights, the actual values of the measure, you can think of as sort of lengths of certain edges on the simplicial complex. So here's just a picture I'm going to flash at you for how that might work, is that I consider a measure on two finite sets, and here's some weights so everything else, the measure is vanishing. So here y1, y2, and y3 are elements of some finite set, and the measure only vanishes along this, is non-vanishing along this diagonal. And to this picture, I associate a very simple looking picture where the lengths of these edges are given in terms of the logarithms of the weights of the measure. And then I can compute the generalized Euler characteristic, and at certain limits, it encapsulates the actual Euler characteristic of this space, which is 3. So just to summarize, mutual information it emerges naturally as the Euler characteristic of some canonically associated non-commutative space. And in the world of probability measures, this is not non-commutative, it's commutative, and it's just a simplicial complex. And you can actually figure out what the non-local correlations are in the state by just computing cohomology. The point to make is that cohomology is a finer invariant than mutual information because it can detect how things are glued together from this perspective versus how many things there are. So it's just a finer invariant. Okay. Some other comments is that there's a G equivariant version of this whole story. So maybe there's some G equivariant mutual information. And this is actually a smaller part of a much bigger story about the Kasparov construction. So you can replace the GNS construction with this more general Kasparov construction. And this is all related to this correspondence of two categories between some category of C-star algebras and completely positive maps, and a category of C-star algebras and pointed Hilbert pi modules. And as a sub-story of this, in a separate work with Greg Moore and his student Roman Gayko, we're exploring the equivalence of categories between matrix product states and completely positive maps. And the hope is that this has shed some more insight on how low energy effective field theories of lattice systems are topological field theories. So it turns out that a natural notion of an RG invariant matrix product state is a Frobenius algebra object in some category, which you should think of as assigning a topological field theory. So there's some future directions we can think about what happens when we compute these homology of some states that arise from holography. Hopefully you get the geometries you get or something nice. Would this be useful for quantum information theory? It would be cool if we can actually generalize the proof of strong subadditivity, which is a relation between entropies that's somewhat difficult to derive for general infinite dimensional von Neumann algebras. And this was geometrically interpreted. There was a geometric proof of this strong subadditivity condition using the Ryotake-Yanagi formula, but it only works for holographic states. So hopefully this construction can actually give a generalization of that proof to just for general states. As I mentioned, it can produce link invariants. There's some generalizations perhaps of the Poincaré polynomials. So these are just vectors that encode the dimensions of the Hilbert spaces, which right now are just integers, but we should be able to generalize this to holomorphic functions. And there's a whole sort of correspondence of this stuff to non-commutative LP spaces and relative modular flows. And I understand part of this story, but not everything. And it'd be great to understand how that works. And I'm looking for future applications of this. Right now, it's just some very general technology, but I'd actually like to do some very interesting physics with it. And if you're interested and you want to get a handle on this thing, I have some software on my GitHub webpage you can check out. Okay, that's it. Thank you.
Okay, thanks very much, Tom, for this nice talk. I'll unmute everyone so we can clap. And let me mute all again. And other questions? I can see that Hank Chen has a question. I will unmute you and let's see whether you can.
Hello?
Yeah, Hank, you should be able to ask your question.
Hello, can you hear me?
Yep.
Okay, thank you, Tom, for the very interesting talk. So I'm just coming in from a more condensed matter sort of perspective where you were talking about Kapustin's work, right? Where you relate the matrix product states to the invertible 2D TQFT. So just from this understanding where you have these sort of interacting classification of topological orders on the right-hand side in your diagram over there, there's this associated map into free fermions, right? Where we can actually detect what happens to topological order as we take away interactions. Maybe there's, from your perspective, maybe there's also something analogous on the state side.
So you're saying I'm not sure, you're saying the free fermions are somehow associated to this side?
Yeah, on the right-hand side, there is a map. Yeah, so it's in a free Hopkins classification where they actually studied these kind of maps for free fermions. Yeah.
Okay. This is all relatively new. There should be something corresponding there. This is a functorial equivalence. There's a translation of anything on this side to something on this side. So indeed, there should be something on this side.
Maybe I thought that it might be interesting to study that on the left-hand side as well.
Absolutely. That's the whole point of it. Yeah.
Okay, good. Thank you.
Just don't know what it is.
Mhm.
Okay, I don't see any other questions. Perhaps while everyone is trying to get raise hand function to work, can I ask how far away are you from actually applying this to holographic systems? You had on your slide, the next slide, I think.
No. Right. Yeah. So this is all relatively new. I've been just working on the technology itself, and recently my focus is actually on this correspondence, which is somewhat related to the entanglement cohomology. But indeed, that something that we'd like to apply this is just some very simple holographic system to see if you actually this geometry is related to the sort of emergent geometries you get out of holography.
Okay, thanks. I don't see any other questions. Let's thank Tom again. I will unmute you. We will continue at, well, 5 o'clock British summertime, whatever that is, where you are, which means in 20 minutes with Nathalie Paquette. So thanks very much, Tom.